Hello, good morning, good afternoon, or good evening from whenever you're watching this video. My name is Raquel Tipton, and today we are going to go over welding inspection types, and we are going to go over a welding example, finding the design strength in a weld. Okay, so first off, I would like to say all the information found on the welding inspections was found on the largest open access portal of non-destructive testing, or the NDT, website by an article by Charles Hayes, who is an international sales and support manager at the Lincoln Electric Company in Cleveland, Ohio. He holds a NDT Level 3 certification from the American Society of Non-Destructive Testing. So first off, we're going to go over visual inspection. The equipment needed for visual inspection is a magnifying glass, a weld sizing gauge, a pocket ruler, a straight edge, and you need to know what standards you are going by. That can be found in the specifications for a job. So visual inspection is often the most coefficient method, but it must take place prior, during, and after a weld. Many of the standards and your specifications will require this to do this inspection first, because there's no point in ordering a expensive inspection if the weld is not good just by naked eye or just by being able to look at it from a gauge. All right, so this second inspection that we're going to look at is a radiographic inspection. The equipment needed is a commercial X-ray or gamma unit made especially for inspecting welds, casting, and forgings. Film and processing facilities where it's going to need to be processed somehow, and fluoroscopic viewing equipment. This is all equipment that you will have to order from that third-party company when ordering this inspection. This is just an X-ray, and an X-ray can be used to determine the internal soundness of welds. The term X-ray quality widely used to indicate high quality in welds that arise from this inspection. Radiographic is the most widely expected from the NDE methods. It is widely accepted, but your type of inspections that you need will be found in your specifications, but most of the time it is this type of inspection. Alright, our third type of inspection is a magnetic particle inspection. The equipment needed for that is a special magnetic equipment, also magnetic powders, dry or wet form. Magnetic particle inspection is a method of locating deficiencies in magnetic material. This is an excellent for detecting surface defects in welds, including deficiencies that are too small to be seen with the naked eye, so you wouldn't be able to see it with that visual inspection. And these are defects to the naked eye that are both just to the naked eye and slightly subsurface on that weld. Alright, our next type of inspection is the liquid penetrant inspection. The equipment needed is a commercial kit containing fluorescent or dye, penetrants, and developers. You also need some type of application, whether that be in a spray can, painting it on, whatever that means, and a source of ultraviolet light to be able to see those surface cracks and pinholes that are not visible to the naked eye. You can then be able to locate those cracks, pinholes, or leaks in the welds and be able to fix those. Okay, our last type of inspection before we move into that example is an ultrasonic inspection. The equipment needed is a special commercial equipment, either a pulse echo or transmission type, and standard reference patterns for interpreting those videos that you do get. So you'll need something to reference what a good weld is going to be. Ultrasonic inspection is a method of detecting deficiencies by directing a high-frequency sound beam through a base plate of a weld on a predictable path. When the sound beam's path strikes in problem or deficiency in the material, it can then reflect that sound back, and you'll be able to find out where that defect is farther down in the weld, as you can see in the picture I have provided. Both surface and subsurface defects in the metals can be detected, located, and measured by that ultrasonic inspection. All right, now it's time to move into that example. So we will be solving the following example. A fillet weld is used to connect the members shown below. Determine the LRFD design load that can be applied to this connection, including the plate. We will be using U equals 0.75. Some of our givens are, we have a 1/4 inch weld diameter. Our plate is a 572 grade 60 steel with an E80 electrotides. Problem. So first we are going to write out our problem statement with our givens. Those givens can be found up here. You can see them. And then first we're going to check the weld length size ratio. To do that, we're going to take that 6 inches divided by 1/4 of an inch. So that 6 inches comes from that leg of the one leg of the weld. We're going to divide that by 1/4 of an inch, which is the weld diameter. That equals 40, which is less than 100. So that is going to mean the B equals 1, which in most situations that B is going to equal 1, but we're still going to check it. So then we're going to find the weld strength. For this, we're using phi equals 0.75, which can be found on page 307 in your textbook. So for that equation, it's going to be phi times FNW times the AWE times B. So first to find that FNW, we're going to do 0.6 times FEXX. So that FEXX is part of that E80 that we were given, and the E80 means it equals 80 KSI. So for that equation, it's going to be 0.6 times 80 KSI, which equals 48 KSI. That is the new KSI that we're going to be using for this equation. Next, we are going to do the AWE, which is going to be the weld diameter again, times sine 45 degrees times the length. So first, that length is going to be that 10 inches, again, that leg that we used earlier. Just one leg, but we have two, so we're going to multiply that by 2 legs. And so that brings it into the equation of a 1/4 of an inch times the sine 45 times that in the 20 inches, which equals 3.54 inches squared. So we can now plug that into the equation, and it's going to be 0.75 times that 48 KSI times that 3.54 inches squared, which brings us out to the weld strength to be 127.44 KSI. Alrighty, now we're on to step 3. We're going to check the yielding. The equation for that is phi times the yield strength times the gross area. So we are going to first find the gross area, which is going to be the gross area of the plate that we are welding on. So that is going to be 3/8 of an inch times 8 inches, which is going to be 3 inches squared. Then we can, we already have all the other givens. The FY was given, was a given we found earlier, which is that 60.2 KSI. And then, phi is 0.9 for yielding. So that will bring us out to a, yield strength of 162.54 kips. Next, we are going to check the rupture. The equation for that is phi equals the ultimate strength times AE. So first, to find AE, we're going to use U times the gross area. U earlier, as I said, was 0.75 times the gross area of 3 inches, which comes out to 2.25 inches squared. Sorry, I didn't put the units on there, but it's inches squared. And then we can then plug that into the equation. Now, this is the last test that we are testing, so we're about to put this all together. Just hold on with me. So that is going to be 0.75 which is the given for phi for rupture, and then we're going to multiply that by 75.4 KSI, which was the ultimate strength given, times that gross area of 2.25 inches squared, which comes out to a ruptured strength of 170 or 127.20 or 23 kips. So now we have all three. We can compare them. So when comparing all three of these, we are going to choose the smallest one. As you can see, we have pretty close with the first and the last one, but we're still going to go with that least one, which is the controlling capacity. So that rupture strength will be the controlling capacity of 127.23 kips, and that is your answer to the problem. Thank you for watching.